And we are indeed live. Okay, so welcome again. Right. For anybody who doesn't know, my name is Valentin. We also have Tim Bessard on the call, who is the... Oh, Tim disappeared again. We lost people. Okay. Who is the main author of CUDA Native. I maintain kernel abstractions and cassette and other tools in the GPU ecosystem. And so what today is more about is I wanted to know what people are using in the ecosystem for tools, what they particularly like about the JuliaGPU offerings, what if they have questions. You feel free to ask me any questions you have. And yeah, so maybe let's do an initial round of introductions. Lucas, do you want to start?
Hi, I am Lucas Wilcox. I live in Monterey, California, and I work with the Clima project, where we use JuliaGPU to do numerical PDEs.
And
yeah.
Tim, do you want to introduce yourself?
Sure. I'm Tim. I'm from Europe, Belgium, Ghent. I'm at Julia Computing, working on many of the GPU backends that Julia currently has to offer, most notably for the CUDA backend, but currently also for the Intel backend, and doing some other general compiler work to support the various GPU backends we hope to be having soon.
Cool. Right. So for everybody else, maybe Rick, why are you here? What do you do with JuliaGPU?
Good question. Why am I here? We'll go straight to philosophy. No, I'm a geophysicist. I'm working in a small company environment, and one of my overall tasks right now is to try to, within this environment, encourage people to look at Julia as an option for doing machine learning, which is becoming an increasingly important objective. And so one of the reasons I wanted to be involved with this or check out your office hours is because even though we've had some code running with Flux and so on, we've been building with relatively small problems. And so I'm at the point where I'm trying to use our internal hardware to run things with CUDA in the GPU, and I'm hitting roadblocks because it's not loading. And so I've been scanning the docs trying to figure out, okay, how do I decode an error, which isn't really helping me. And so I'm trying to get feedback, but I'd like to get feedback, but also, I do have a very practical question. I can't even make CUDA load and run right now. And I'm just, any tips on doing that would be wonderful.
Okay.
How to figure out what the problems are. So yeah, that's just my introduction. So
yes, we will get back to that once we are done with introductions. Thank you.
Okay.
Nitin.
Hello.
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 Would you like to introduce yourself?
Can you hear me?
Yes.
Yeah. So I'm Nitin. I'm from India, and I used to work in MATLAB for most of my programming. So, but since it's lockdown and we are working from home, I don't have access to MATLAB. So I was searching around. I came across Julia, and it's kind of nice. So I am still in the process of understanding how to write GPU codes and how to basically use the GPU to leverage much more performance. So yeah, here I am. I wish I find something interesting in here.
Thank you. Okay. Brian Chen, would you like to introduce yourself? If not, that's fine as well. Okay, no worries. Then let's maybe you can write a brief introduction in the chat, and James can introduce himself while we carry on.
Right, you guys can hear me, right?
Yes.
Okay, I'm working with Lucas and Valentine, mainly on Klima stuff, which is Lucas mentioned earlier. I've got a history doing GPU stuff. I kind of just wanted to hear what everyone was up to today. I don't have anything specific, so.
Filippo, do you want to introduce yourself?
Yeah. Hi, everyone. I'm Filippo. I'm a postdoc at the Flatiron Institute in New York, even if I'm stranded in Paris right now. I work in physics. I apply machine learning techniques, neural networks to try to represent quantum systems. I joined it because I recently tried to starting wrapping metal to expose an interface like, say, Q arrays, rock arrays, a bit for fun, let's say, not really for because I need it. I mean, I would like to use it, but so I have been bugging Tim and Julian Samaru, who told me just to chip in, and we might discuss a bunch of things here. So that's why I'm here.
Cool. Yeah, the metal work is very exciting. It's been if you can get it to work, that would be amazing.
Yeah, let's hope so. Let's see.
Diego, do you want to introduce yourself? No, okay. And the last one on the call right now, Viber, if I pronounce the name correctly.
Yeah, it's Vaibhav.
Viber.
Yeah. So I am just here to hear people talk about things. I want to know what's going on. Yeah, nothing too specific.
Okay, cool. Well, right. So so one of the questions I had is if you're writing GPU code in Julia, how are you doing that right now? In general, I would say we have core arrays and similar packages like in the GPU arrays realm, rock arrays coming up. And they offer an array-like interface where you most of the time don't need to worry about being working with data on the GPU. Then you have CUDA native as a programming option, which allows you to write high-performance GPU kernels with all the bells and whistles that the CUDA programming model gives you. And then there are compatibility packages. So GPU arrays used to be one of those. Then last year I wrote GPU-Phi loops, which is now, by the way, end of life and is going to be replaced by the new package I'm working on for Klima and other HPC applications called kernel abstractions.gl. So for me, it would be interesting, like to hear if you are writing like low level, or if you're writing GPU code, are you mostly just using flux and arrays, or are you actually writing directly writing code for the hardware?
I guess I can start and just say that I'm kind of using, I'm not really using Flux at all. Just saying I'm pretty much writing stuff in kernel abstractions, CUDA native, this type of stuff. But also my applications are very much, linear algebra specific. So.
Yeah, as I mentioned a little bit earlier, my primary interest right now is working inside of the Flux environment. There are certainly longer term goals for using GPU at various points for matrix operations, whatever, different kinds of calculations, but Flux is definitely the main interest right now.
Okay, cool.
Yeah, as you know, kernel abstractions, mainly what I write.
Well, I have to say, Lucas is the reason why kernel abstractions exists. So.
Yeah, and I'm interested in a kernel abstractions based array because I use array stuff a lot.
Yeah.
And I'm interested in what you guys are doing for the different backends so that we can hook kernel abstractions to all the new exciting hardware.
Wait, could I ask, what do you mean by kernel abstractions array, and how is this different than like a coup array? Sorry.
So I was trying to do like a structive arrays. Trying to bring back something Valentine did a while back. And yeah, I was ending up having to re-implement a lot of coup arrays inside the structive arrays. So like your reductions, prefix sum, or these types of things, I'd have to rewrite myself. But if we had like an abstract kernel abstractions array, then I could just subclass from that and then get the kernels.
Is there a way to use like adapt or something? Oh, never mind. Valentine, Tim can probably.
In general, I think Tim and I have discussed this a bit. In the long term, we would like to, once kernel abstraction has stabilized, we would like to move the algorithms that have been implemented in GPU arrays over to it. So that there's a lot of the implementation is there in generic. These are algorithms that you could execute on the GPU, but they are backend independent, and then provide performance specializations through coup arrays. But yeah, that requires some thinking because the programming models don't quite align perfectly. Right, kernel abstractions is event-based, and GPU arrays is implicitly synchronized through the default stream.
The hierarchy is there already, though. So in terms of extending on an abstract GPU array type, that's 100% the design goal of GPU arrays.jl. But as Valentine mentioned, in the future, we hope to be able to ramp up the development that happens there and base it on top of kernel abstractions. But currently, it's actually pretty powerful. There's a fair lot of well, not advanced, but non-trivial GPU algorithms implemented in GPU arrays, and there's some infrastructure there as well to inherit based on that and to share some functionality across devices. So I don't think we need an additional kernel abstractions array, or at least I hope we do not.
Yes, that would be more. I think that would be additional maintenance burden that I would like to avoid.
So then we need to extend GPU arrays to be able to take more than just a basic set of types as entries. I mean, that's what I ran into when I was trying to do
basic set of types. What do you mean by that?
Yeah, I think it's. I'll have to look at it again, but I think it has it baked in that it, the entries of the array are only float 64, float 32.
I don't. Okay, we should look at that offline.
We should look at that. Okay.
Okay, but just as a note, GPU arrays used to be concrete. So you used to be able to instantiate a GPU array. That's not the design anymore. The new design is that the GPU array, an abstract GPU array, is like an abstract array. It's just an abstract type and interface. And we need to document thoroughly what this interface requires from downstream implementations, but you will always still be calling the downstream constructor.
Okay, I didn't know that it's now abstract like that.
Okay.
If anybody has questions, just shoot, throw them in the room. I think that's the easiest way to get a discussion up and running.
Yeah, well, since my question's maybe really very basic, maybe we can start there. I'm in the spirit of office hours. Again, I'm really just trying to get going using the CUDA stuff for inside Flux on a Linux workstation. And, I've got the CUDA.jl docs open and, I've installed the packages and so on, but when I try to run it, it gives me some error messages that I can't resolve, which I'm guessing maybe due to the version of the libcuda that's installed on the system. But it would be great to get a little bit of insight into how to decode these things. Maybe for the documentation, for example, it says you need it mentions artifacts, but I can't figure out how to get the artifacts installed. Because it'd be nice if it was all sort of built into the Julia system, so I didn't have to mess with the system level things. But it's not entirely clear. So.
It should be actually. So the goal of artifacts is that CUDA is automatically downloaded and installed. The only thing that you still need, and we cannot possibly provide, is libCUDA, which is the NVIDIA driver.
Okay.
So, well, I'd say show the error message, or yeah, I think without that,
yeah, I can do that.
You have to comment on it.
Sure. Yeah, no, I was going to say maybe I could read it, but that would be a heck of a lot easier to share my screen for all of us. Okay, so it's okay. Is it displaying yet?
Yeah,
it is.
Okay. So there is a libCUDA installed on the system, but I'm guessing it's an older one. And again, I'm not sure what version should be installed.
No, this is
actually, you can see right here. These are the versions which are installed.
You are using a too recent libCUDA.
Ah,
not match. Yeah.
Okay. Darn, that's usually not the problem. Okay. So what version do I need? That's
hard to tell. You need one that matches the kernel module you have currently loaded. So I'm not sure, are you on a cluster or is this your local machine?
This is a standalone workstation right here. Just a
yeah.
It's CentOS 7.
Upgraded CUDA without rebooting, and as a result, you have an older kernel module loaded.
Okay, so the Linux kernel module is what you're referring to there?
Yeah, so what you see at the end of libCUDA for 40.64, that's the version of the NVIDIA driver. And that needs to exactly match up what's installed and what's currently loaded. So if there's a mismatch, then you get this nice error, which indicates that there's actually some sort of forward compatibility, but that only applies if you give lots of money to NVIDIA and buy their Tesla hardware, which you haven't, and as a result, you get this error.
Well, okay, so as I mentioned at the very beginning in the introduction, we're a small company, so we don't really have any centralized support. So things are kind of sometimes installed haphazardly, shall we say. So I don't even know the history of who are, obviously somebody installed it around March 20th, it looks like.
Yeah, sure. So this is an error thrown by CUDA. We don't do much. Okay. So as you can see in the background, we are just calling the initialize call, and then CUDA fails, and we actually haven't executed any code yet.
Okay. So again, I've not been just for another piece of background. I usually work on my Mac laptop, which of course is the Radeon stuff. So I'm not really even used to diving into these things here. But do you have what would I do to find out what the right version is? Again, you mentioned the Linux kernel and they should match, but I'm not sure what to do. Is it easy to say what I should look for? Or?
If there's a mismatch, it should be listed in DMSG, but generally, though, you should just use your package manager to inspect and see how you've installed the NVIDIA driver, because there's a variety of ways you could have installed it. You could have downloaded it for the NVIDIA homepage. You could have used your package manager. So yeah, it's hard to give you one clear-cut solution.
Okay, no, but that makes sense. I can go back to, I'm guessing that somebody just went to the NVIDIA webpage and downloaded something and said, let me put this in here. So I can easily go back to the package manager and go from there. So that makes sense. But at least it helps a lot too to know that that's a library which is too early or too recent. Again, usually my problem is running in circles trying to find something that's up to date. But okay, that helps a lot.
You said you're on CentOS 7, right?
Correct.
There are a few guides online to help you through the process. They're usually quite rigorous for CentOS 7, not CentOS 8 though.
Okay, yeah, no, it took some effort to get the powers that be to be willing to go from 6 to 7. So 8 is a long ways off.
Yeah, I know that pain.
Yeah. Okay, but yeah, so I can Google around for CentOS 7 NVIDIA configurations and look at the package manager and that kind of thing. That makes perfect sense.
Yeah, right. Specifically, a guide for setting up CUDA should help you with this.
Okay, cool. Thank you very much.
And if you have any other issues, feel free to jump by the Slack GPU channel, and there you can just copy paste an error message, and we'll be able to help out probably.
Okay, cool. Great, thanks.
So how many people are actually interested in running GPU codes on Macs?
I am, but I don't have a Mac, but I'm still interested in it.
Older than me?
Yeah, I would also be interested in that.
Okay, so Julian Summerall just joined us, and he is maintaining the AMD GPU backend. And since Apple and NVIDIA are not on speaking terms, quite literally, in general, like the Apple has deprecated support for OpenCL, which is a shame. And so, like the only way forward I can see is to go through Metal, and Filippo has been starting to experiment with that. But yeah, it's something I don't think neither Tim or I have looked at, or Julian, because we are not Mac users. We primarily live on Linux land.
If you need people who want to use GPUs on Mac, I know people who want to use GPUs on Mac.
Yes, but they need to be willing to debug it.
Yeah, maybe they'll let me borrow the Mac for a week, and then.
Okay. Well, I've seen a little bit of activity on the Slack channel recently that some people are starting to try to dive in to get things working with Metal.
Yeah.
For better or worse, which seems to be the way to go. And I did volunteer. I said, I'm probably not the person to be doing the raw development, but I'm happy to test. Got the hardware, got my nice Radeon thing here ready to crunch away at things.
Yeah, well, I mean, that's good. So this is Julian. So Filippo, you're on the call, right?
Yeah, I'm here.
Okay. So you had a question about just how code generation works in general, what the compilation pipeline looks like, which is something that's generally important to know when you're working with this sort of stuff.
Yeah.
Is there any area in particular you don't understand, or Valentine, do you think it would be okay if I gave like a quick overview of how the pipeline worked? Okay. Okay. So just in general, and I'm speaking as someone who's picked this stuff up recently in like the past year or two, so I'm not an expert. Tim and Valentine are the experts, but the way that GPU code gen works in Julia is that it's a little bit different than regular Julia execution. So regular Julia is very much based on like kind of dynamic execution, where you have dynamic dispatch, you have, you generate some code, and then that code kind of gets stuck at some point, it can run a portion of the code, and then at some point you don't know the types for your arguments when you're going to call a function, and then you call back into the compiler compiles some code, hands it back, and then you jump to that code and you kind of go through that. In GPU land, we can't exactly do that. So you pretty much have to compile everything ahead of time. And so for anyone familiar with using CUDA native, I believe it's the @CUDA macro is what you call to pretty much say, okay, here's, let me hand you a function with some arguments, and I want you to compile that for GPU usage, for GPU execution, and go run it on the GPU, pass the arguments in, and then that's that. Can't return anything from it, but you can pass in arrays and then do in-place operations on those arrays to you know, get the results back that you need or to do the operations that you need. So starting from that macro instantiation, what pretty much happens is that we ask Julia, we do a C call into Julia and say, hey, here's the specific method we want to call. So, you know, the specific instance of the function for the given concrete arguments that we've passed in. Maybe you've passed in, you know, 2 arrays, maybe Q arrays. We'll just go based on, you know, the CUDA approach. And, you know, everything is pretty much specialized based on those. So you know the specific method you care about, and then you know all of the arguments, their types. And assuming all of that is concrete and a method exists for that, Julia will hand us back some LLVM. It'll say, here is the definition for the function in LLVM. Do what you want with it. And now from this point, this is where things have changed a lot over time, but the general approach kind of still holds. We'll do some work in the new GPU compiler.jl to set different things up, like do optimizations. We'll change like the LLVM function definition to be correct for the so-called backend, the kind of the instance of the compiler in LLVM that's specialized for emitting native GPU code for the type of GPU you're targeting, whether it be like the NVPTX backend that CUDA native uses, or the AMD GPU that AMD GPU native uses, etc. And anyway, so we go through all these things. We may see this part happens. So there's some parts that kind of Julia handles for us automatically. Like, you know, if inside your kernel function, you call another function, maybe you call the sum function on 2 integers. Well, Julia already knows what the code for that looks like. You know, Julia looks all that stuff up for us. Other things like runtime intrinsics, things that are specific to the GPU, and things that they're not necessarily something that you can write as generic Julia code exactly, like they wouldn't work on the CPU. Those we implement kind of in a slightly different way, and we explicitly inject into the LLVM module for the code. So anyway, we do all that sort of stuff. Once we're done with that, go ahead.
Can I just, I have 2 questions. So
yeah.
What you get from Julia and you feed to the GPU compiler is LLVM bytecode, right?
Yeah, what we ask Julia for, and what Julia also asks kind of LLVM for in a way, is LLVM IR.
Okay, great. And a second question. So can you give me an example of one of such things that you cannot represent in standard Julia CPU code and you need to inject into?
Yeah.
Just to have a better idea.
Yeah, so as an example, if it's not that you can't represent it in Julia, it's just that it's not valid, say, on a CPU. One of those things would be, let me think. So allocation support for say, like if you use static arrays in a kernel, you're kind of statically allocating, in quotes, on the GPU. And in some cases, you actually need to dynamically allocate memory. Like in CUDA, you can actually do like a device-side malloc. You can allocate memory for a kernel. And what CUDA native does is it checks for those calls, and it replaces those calls with a call to CUDA native's implementation of malloc, which actually, to my understanding, forwards to CUDA's malloc. And so that's something that's done after we've already asked Julia for the LLVM code, and like Julia's compiler is, in a sense, not really involved in that. We're the ones who actually have to do that replacement, or CUDA native has to do that. there's other things like some things are partially handled by Julia, but they're specific to the GPU, which is things like indexing within a kernel. If you need to ask, like, you know, like when working with GPUs, you're typically working in sort of like a grid operation. Like you may have an X and possibly a Y or Z dimension, and you can ask the GPU, what dimension am I currently working on for a given thread? Like, what is my XYZ dimension? What is my XYZ index? What is the XYZ dimension of the blocks and the threads? Stuff like that.
Okay, thanks.
Mm-hmm.
Because, well, okay, I don't want to monopolize the discussion, but like this is somewhat, I mean, I'm just trying to relate this to the OpenCL or Metal programming model, where basically you have, let's say, kernels, compute kernels. You feed them a bunch of, let's say, buffers, so input and output arrays. So one thing that I noticed going through, let's say, all of this, like through the source code of rock arrays and Q arrays, is that I mean, you often look for the I've asked you that already, but you often look for the root pointer of a buffer. I'm not really sure I understand why is that, because I mean, to write valid code, you never need to have a root pointer to any bunch of memory, right? You can just move over those. So
yeah, so I guess I'm not exactly sure how Metal exposes that, since I guess it's typically written with Object-C in mind, and so they kind of have like opaque objects.
I
when
think
you're
it's very
working,
similar to OpenCL. Like it's very similar to OpenCL in that regard, I think. So
like where you pass
have
an object.
Yeah, exactly.
Yeah. So in every case, even if you have an object of some sort, that object will eventually contain somewhere a pointer to the actual buffer of memory. And at least in non-metal cases, so in the CUDA case, in the HSA case, you pretty much just are basically passing a small struct that has the pointer and has the size, so that you can actually operate on that data. Like you need a pointer so that you know where is my data and how do I access it? How do I do loads and stores? And if you don't have a pointer, you need some way to access that data. So if Metal doesn't, so there needs to be some way to just index through memory and load and store. That's the main thing you need. You don't necessarily, I guess, need a raw pointer, as long as Julia knows what the offsets of the structure, the buffer structure being fed in are, like where in that. I guess you kind of do, though.
In general, like if there are some intrinsics that you can just feed an object, which is not a pointer, but something like a pointer, and you can say, give me an index to this thing. The only thing you really need is a way to translate a Julia representation of that to something that works with that intrinsic on the GPU.
Exactly.
Like if Metal has a multidimensional array index and you're giving it an array object or something like that, you don't need to give it a pointer. You only need to forward it to that instruction. So I don't quite know how Metal exposes its like data accessing and storing patterns, but it should be fairly flexible in that regard. Yeah. I mean, a pointer is just basically that object. And then we add some metadata to it so that we know these are the sizes and the dimensions, so that we can do things like checking bounds on the GPU. So for me, that's an important bit of the JuliaGPU approach, is where we're trying to be as much like Julia and as similar to Julia semantics as possible. And that includes things like error checking for bounds checking by default, and you have to opt out of it. So if you write GPU code in any of the compilers, you basically need to say add inbounds if you want to avoid that check. That is different from how, as example, CUDA-C would work, but it's closer to how Julia programmers are already used to writing code, and it allows you to use the same programming model in there, like the same headspace to write code for the CPU and GPU.
I see. But basically in Metal, what happens is that, let's say you don't have a same source approach of CUDA, unfortunately. So basically you can allocate buffers, which are given to you just as opaque objects that you can bind to your kernels before execution. So you say that the first argument to the kernel will be that buffer, the second argument to the kernel will be that buffer, and so on and so forth. And when you execute the kernel will, once it's launched, he gets pointers. But let's say in the host, you never have access to the raw device pointers. But then on the inside of the kernel, you can do anything you want. So I mean, I don't see.
So that's generally speaking fine. So I think the only thing that would, so right now in QArrays as an example, what we allow is for an array index to happen from the host to the GPU. And we do that by issuing a mem copy. So we are issuing a CUDA driver command and say, copy this 1 byte, these 8 bytes of memory and to the host. So you don't need a pointer to do this access. You can do that in HSA much more directly, but generally speaking, you don't need on the host side a pointer to your array. It's just that CUDA represents arrays on the host as pointer as well.
Yeah, but I had noticed just that it's a bit of trial and error for me to like delving inside of a source of those packages to understand a bit how they work. Yeah. But I mean, I implemented the same functionality by just basically what you do is you copy from the buffer with an offset that is, let's say, just more or less a pointer.
Exactly. That is exactly what you need to do.
Yeah. So I think I feel like I'm catching all the time now. My question is more about how to get started into like how to plug into the compiler tool chain and start to see what can be done. So I was just trying to check if I have everything we need. So yeah, this one looked like something that I really cannot do easily. So
I think what we probably need to do is if we have, I'm sure you or someone already has one, but we need like a simple example of like SPIR-V or LLVM-IR for a simple kernel that we know works on Metal, say through the typical Objective-C route, but that or whatever, just something that normally works on Metal, and we can kind of dissect that and see what operations are done on the input arguments, because LLVM-IR and SPIR-V, it's a standard representation we should be able to read it and see, oh, okay, here's where the offset from the actual argument passed to the kernel is, and we can infer what the structure is if it's not already documented. And once we have that information, the thing is, like, most of these things, like CUDA, like HSA, and I'm sure like Metal, OpenCL, whatever, they all really use pretty much the same approach because they're interfacing with, pretty standard hardware. Like, we're not dealing with special, very weird GPUs. So, and, the OpenCL paradigm and the CUDA paradigm are pretty much the same thing that everyone copies. So in terms of how the internals actually work of those things, it's pretty much all the same. So it shouldn't be too hard to figure out like what the correct, like what the pass-in buffers, like what they actually look like on the device, what are the offsets of the actual buffer, what are the sorts of operations that you see typically done to load a value from a buffer, store to a buffer. And with that information, we can probably help you figure out like how to get that basic kernel set up from actual Julia code, like actually write that in Julia, compile down to the same sort of structure, and then get that launched onto the device. So I think we're probably almost there is what I'm trying to say.
Yeah, I think the step that we need to figure out is, given an LLVM-IR, how do we get to Metal? And if that is going through SPIR-V or if that is going through some other way. I think that is the big thing that we need to figure out before we can talk about, okay, this is the calling ABI for Metal kernels.
Yeah, exactly. Because as I think it was you that mentioned on Slack that Metal uses an older version of LLVM, so they're like the bytecode is not really, the IR is not really compatible.
So I mean that was from a year ago or so, the information. They might have upgraded since then, but in general they're using a modified LLVM that is internal to Apple, and so we can't just emit LLVM bitcode.
So that means that we have to, like, one option is to pass through SPIR-V, right? So that might work.
I think that's the easiest way, that you just take the SPIR-V compiler as soon as we have it, and then you cross-compile with SPIR-V cross to Metal sharing language, and compare that output to some known good kernels, which you can interface with, and try to get to a point where custom Julia code can get compiled. Well, that's basically how I approach the problem with one API at this point.
Okay. And does your branch work, or is it still a work in progress that I cannot really work with, so I have to wait for that?
I'll try and get it in a shape that it works again this week. Yeah, I'll ping you at that point. I have some other priorities right now, but I'll try to get it working by the end of the week.
Okay, so like right now, if I pull it, it won't work, so I wouldn't be able to.
It will work, but you'll have to use an older version of one API and GPU compiler.jl. It might be a bit finicky to get working, but if you have the time, then I can definitely help you get it working earlier than that.
Sorry, I didn't catch what you said.
If you want to get it working and you have some issues, just ask me or let me know, and I'll be able to help you then.
Okay. Yeah, thanks.
Cool. Do the other folks have any burning questions right now? We are coming up on the hour. So if you have any quick questions, that would be the right point to ask now.
Well, I don't have any questions, but I do have to take off also. I know we're coming up to an hour, as you say, but I do want to say thanks for offering this. It's been very helpful for me, both for my immediate pragmatic task, as well as for hearing a little bit more about the discussions of how this works in the Julia context here. So thank you very much.
Thanks for joining. And as Tim said, we are hanging out on the GPU Slack channel and answer questions there at all hours of the day. Then I would have maybe a bigger question for people to give feedback on. Right now, we are planning to do this every 2 weeks. Is there something like, I like open discussions, but is there something you would like to see us do in one of these sessions?
I actually might personally like, I know that there are some new performance tools that I just haven't dug into yet from NVIDIA. Like I'm still using NVProf. I think I need to update that and stuff like that. So maybe, I mean, I can look into this myself. Maybe this would be useful for people doing like performance analysis and stuff like that. I'm not sure.
Right, so we could certainly do presentations about certain topics like performance analysis, like how to get started.
I think that would be very useful. If it were me, I'd suggest, I like a sort of a hybrid approach, maybe if it's a 5 or 10 minute kind of kickoff presentation or live coding kind of demo. But it's also good to have plenty of opportunity for discussion. So, okay.
Yeah, I think that would be good. I'd also like just like a brief introduction of where people are going with their work every once in a while, just so that we kind of know what's moving. Maybe we'll get that implicitly through the discussion. But
yeah, so a state of the ecosystem, basically.
Yeah.
Right. I think the big news is we're working on more backends.
Yeah, I'll try and give a demo on the profiling tools. Maybe that would be useful for people who could profiling tools. I think that's a good suggestion.
I can also give an introduction to kernel abstractions.
Oh, there was a question in the comments for you, Valentin, about whether GPU compiler would ever use MLIR instead of emitting the MLIR directly.
Maybe. So I'm working with Leon Shen on an experiment to see what a compiler infrastructure for Julia with MLIR would look like and what benefits we would get from it. And MLIR right now is doing a whole bunch of experimenting about how to compile for GPUs, how to represent parallelism, and how to express new ideas in compiler design and move behind the model that LVMIR is basically modeling C. And so how do we express things that are not C-like? How do we do optimizations in a compiler that are about higher level operations like matrix and tensor operations, but how do we also similarly reason about loop nests, do polyhedral optimizations? How do we reason about different memory locales, like memory that resides on the GPU or resides on the CPU and needs to be moved, batched, etc. The question is, will we get to the point where we can say, instead of emitting LVMIR, we are emitting MLIR, and then we are using those tools to target various GPU backends? As a prototype, probably. As a long-term stable thing, it would require, I think, a lot more investment into the technology chain, because we are no longer reusing the LVM compiler from Julia. We're no longer reusing that output. We are starting at an earlier stage and translating that to MLIR. And so you need to implement a lot more code to get the same set of features. So maybe, certainly for prototypes, I hope that like in the fall we have some cool demos to show that you can actually do that. But in practice, to run large scale systems on it, I don't know when.
It also seems a slightly higher level abstraction to parallelism. So if users at some point get used to getting all of the flexibility in programming the GPU with low-level Julia code, as some abstractions that we've implemented require, then MLIR might be a step back, depending on how the model of parallelism actually will materialize in MLIR. So that's not clear at this point.
Yeah, it is interesting, so because you can, in theory, emit MLIR, so you can intermingle in MLIR dialects with each other. And so you can emit the low-level GPU dialect at the same time as you're emitting your high-level dialect, and then co-optimize them and successively lower them down to LLVM, and then you end up with something. So you can actually access a lot of low-level functionality from a high-level dialect as well. But we will see. Right now, Brutus, as an example, is a C++ library instead of a Julia library. And a lot of the thing that is really nice about the GPU ecosystem as it is today is that it's almost all written in Julia. There is no C++ shim that we are using. There's no C++ library that we're using to talk to LLVM. It's all based on LLVM.gl. And that makes it a lot nicer for people to start using it and to contribute. Like, I don't think we would have AMD GPU if we had written CUDA native in C++.
You're right about that.
Okay. Well, thank you all for attending. And I hope to see some of you in 2 weeks.
Yeah, thanks for doing this.
Thanks a
Thanks for
lot.
doing this.
Thanks a lot.
Have a good day, y'all.